Kia ora koutou and welcome everyone. We are really happy to see you here today for the launch of our SESOC webinar series. Jenny Tibbler and I have been working very hard with the hope of delivering a good stream. And it's fantastic to see such great interest from our members. This is just the beginning and we're excited for what's to come. Our hope is that these webinars give you useful and practical knowledge, and we'd love to hear from you the ideas for future topics. So please feel free to reach out with any suggestions and any questions. Today, we're lucky to be joined by Des Bull. Des has contributed enormously to structural engineering in New Zealand, particularly in concrete and seismic design. He's also the recipient of the SESOC President's Award 2025 this year, a well-deserved recognition of his impact and dedication to our profession. So please join me in welcoming Des Bull.
Good morning, everyone. Thank you for the introduction, Julio, and here we go. It's the title Structural Behaviour of Rigid, and I question mark that because we're going to talk about flexible diaphragms as well, of reinforced concrete diaphragms with a focus on precast floors and seismic performance. I mean, you guys can read that. Just a quick acknowledgement to SESOC, Earthquake Society, Concrete NZ and EMBI, and the numerous research students and academic supervisors of the last 30 years, and a special acknowledgement to Anna Philpott and Dr. Deborah Shearer of Holmes, for whose slides I have largely poached. What we're going to cover today, relatively quickly, is the role of diaphragms and diaphragm forces and key load paths, how precast floors behave during earthquakes, a clear, hopefully, breakdown of the modified Hrenikoff method for the grillages, tips on how to apply SESOC's methodology, which is out of yellow C5, and a practical step-by-step approach to design process, which I think will be familiar to all of you. The first thing we are going to point out is that diaphragms also have to support gravity. So I just sort of put that up to remind everyone, don't forget about that. Often diaphragms and collectors are treated as two, one's diaphragm, one's a gravity support. They're actually doing the two jobs at the same time. Diaphragms distribute inertia. They also tie the structure together. All the vertical lateral load resisting systems are tied together by the diaphragms, and those systems behave because the diaphragms constrain them to all move together and to form with the earthquake. Obviously, one that's not regularly written up anywhere, unless it pops up in seminars, is this aspect of diaphragms. When a column or a wall is pushed out of plane, out of the building, plastically, yielding at the base of the wall or column, it has to be pulled back upright and through to the other side, half cycle of displacement in the other direction by the diaphragms. So you've actually got the diaphragm acts as a large tension device to pull the walls or the columns through the outer plane motion. That's not written up anywhere, but those forces can be really large. So inertia forces give us accelerations, and accelerations give us displacements, and displacements give us these things called transfer forces. This is a slide familiar to you all, I am sure. What we have here is the, I'll just put up the, bear with me, laser pointer. Here we are, that's better, I can find it now. When we have a frame or a wall behaving in isolation, they have their own deformed shapes. When they're slaved together by the floor diaphragm, they have a common shape, and that results in significant forces on the floors through this effect of making the two different structures conform to the same shape. The example says walls, but this also applies when you have frames of different stiffnesses and strengths in a multi-frame system. You'll also get the same form of transfer effect between the diaphragms. The ones that are most familiar to us all are large tower buildings with basements, and this particular, the ground floor, the main backstay diaphragm, as it says, picks up huge amounts of forces as a result. And for example, one of the ones I was involved in Wellington back in the 80s, that ground floor slab was 400 millimeters thick to be able to deal with the transfer or backstay forces. Another spot where we have similar large forces can develop is the transition between podiums and tower blocks. And that roof area there is a significant transfer diaphragm. So we have inertia forces, transfer forces from the interaction with the vertical elements. But we also have other forces that can pass through the diaphragm, such as soil retaining forces, hydrostatic forces, and secondary structures such as canopies, external stair and lift towers, which are external from the architecture but tied back into the building. These all produce large forces to be transferred through the floor plates. On rigid and flexible diaphragms, I'll just read out the first line. For the analysis and modelling of diaphragms are typically assumed to be rigid. That's the traditional way of doing it. Funny enough, it's not a particularly good representation of actual diaphragms. And rigid diaphragms only really apply in one case. And that's the case where you have an earthquake in this direction. This is a moment-resisting frame, concrete moment-resisting frame, and it's only got frames and or walls on the perimeters. This is the only time that rigid diaphragms are basically okay to use, because we've got no secondary frames or walls in the middle, so it's pretty simple. Same building, but in the other direction, we've got primary walls or frames on the perimeter. We may have some frames or walls down in the center, secondary frames. And if you had a rigid diaphragm model for working out the forces in the vertical systems in your computer model, what it does is it overestimates the forces which arrive in the primary elements and underestimates the forces arrive in the secondary elements. And if you think about if you're doing an assessment, for example, maybe it's frame action, maybe it's wall shear stresses, maybe it's the tension tie and the collectors running into the ends of the walls, you will overestimate the force demands on those elements if you use a rigid diaphragm. There is guidance on what a flexible diaphragm is in the standard, but personally I think it's rather dubious and really only applies to that case one. Recommendation is that model the stiffness of your diaphragm along with your beams, collectors, walls, EBFs most of the time. That's model the stiffness of the diaphragm to get a more realistic distribution of forces between this in the system. If rigid diaphragms are assumed, you will get very large transfer forces. And it doesn't take much actual modelling of the stiffness, allowing for some actual elastic deformations in the system. I'll come back to that. Try and allow for some actual elastic deformation in the diaphragm. That will significantly reduce the transfer forces. Some people have talked about using plasticity in elastic deformations in diaphragm. Not recommended at all. If your diaphragm becomes plastic, that relationship between the vertical systems changes and can be quite dramatic. So by modelling your actual stiffness, you can actually result in a significant reduction in transfer forces, which is good for the whole process. So we've seen the slide already, but people think inertia forces and other forces, are these applied forces to the diaphragm? Are the forces in the vertical elements the resisting forces? Well, yes, they are. They are in one sense of the whole building. But when we look at it in terms of what we're doing with the diaphragm, we sort of treat all these forces as acting on the diaphragm. Both the inertias and the resisting forces are acting on the diaphragm. And we set it up such that it all occurs at the same time. And the main thing is it's all in equilibrium. This is just like a key slide for some of the slides coming later. So what we have is in terms of within the diaphragm, we have tension and compression forces. The external forces, these are the forces applied to the diaphragm, are the inertias and the applied forces. The applied forces are the forces coming out of your columns, walls, and so forth are being applied to the perimeter or around the boundaries of the diaphragm. Picking the density of what I mean, choosing the density on the problem, meaning is what layout of inertia do we select? Sometimes a big, simple inertia load at the middle of the floor is enough. Sometimes it's grid line bound. Sometimes it's individual little pieces of inertia over an individual part of the floor plate. Every job dictates it slightly differently. This is one of the flags. Put the inertia of the columns, beams, and facades where these belong. That's locate those inertia arrows on and their value associated with the beam, column, stair, precast stair, and so forth. Don't smear the inertia or the mass effectively of those elements across the whole floor plate. You'll find your equilibrium sort of goes out the window a wee bit. Types of forces with respect to the diaphragm. We've talked about the inertia and forces from the vertical system. But the forces that are coming into the diaphragm, this is what this bit is here, the forces that are coming into the diaphragm are the difference in the shear force diagrams above and below the diaphragm in the element. For example, in these purple drawings are the shear force diagram for a column and for a wall, and the steps in the shear forces are the forces, the green arrows, these are the forces that are going in and out of the diaphragm into those vertical elements. I've got the PISA method up here. This is the method we use at the moment. That's sort of under review, but this is the method we use at the moment for estimating diaphragm forces. The other thing to remember is when you do this modeling, a lot of this conversations around modeling is that every column and wall has actions that are going in and out of plane for that column or wall. A lot of people forget to put the out of plane forces in their model and wonder why it doesn't work. Another heads up is that when we come to modal response spectral analysis, I'll just read it out. Response spectral analysis does not help. It provides maxima outputs. These have no sign, a local maxima occurring at different points in time, and are not in equilibrium. Modal analysis is next to useless for doing this sort of analysis because the actions we get out will typically underestimate the floor forces. Here's an example of what we mean. We have a shear force in the column above, in the positive sense, a shear force in the column above, a shear force in the column below, and the difference in the two shears above and below is the force that's going in or out of that column. So here are the 4 steps that we'll be looking at in the design process. This is all familiar to you all, I'm sure. But I've worked through the general configuration, overall understanding of low pass and preliminary strut and design, complete the strut and design, which is the developed design, as well as then we get into the actual detailing, obviously at the last bit. In step 1, the concept design, what we're worrying about, what is our plans, configuration, what's the shape of the floors, where are the large voids, do we have any transfer diaphragms, and the other one was, do we have stepped diaphragms, vertical stepping. This is the time to set ourselves up for success and avoid significant headaches later. And you'll see why, because as we go through the slides. So this is the concept stage. Picking the configuration of your building layout has a huge impact, obviously, on how we get diaphragms to work. Sometimes the architecture is so demanding that we might want to maintain the shape of the building, but we may actually break the building up into separate elements and maybe use seismic gaps or bigger floor plates so the stresses are brought down to a manageable level. If we have an L-shaped building, just remember that this area in here, the red area, is actually behaving like a beam column joint. We don't design as a beam column joint, we do strut and tie, but the shears and the amount of steel that we need in that area, it's just like a knee in a portal frame. It's working very, very hard. Other things like penetrations and voids, these can get in the way of your primary load path. So a bit of thinking at the very early stage on where your locations are for your voids and working with the architect is a way of making sure we have the best chance of getting the diaphragms to work. And I've got an example of this nightmare where the corner's been chewed out by penetrations. Later, if we get to it, later in the presentation, showed how the engineers got around this problem. Thinking about the transfer diaphragms, in this situation, it's a podium roof, and what we have here is the tower is leaning on the floor plate, which is now leaning on the perimeter frames. So the green arrows, the forces coming out of the both frame systems, perimeter and the tower, and as you can see, the blue is the compression struts, and the reds are the tension ties. The other thing to notice, just by the nature of buildings, in the textbooks, everyone says, "Oh, that is a transfer diaphragm." To some degree, all diaphragms have a sense of transfer to varying degrees. Some of them get absolutely hammered, but as soon as you start having this incompatibility of deformation, all diaphragms have some degree of modelling, some degree of transfer, and that's why we model these buildings in 3D to get all these actions out. Transfer diaphragms have some real quirks. Concrete core, perimeter frame, basement. If you have a very stiff diaphragm at this point, you'll find you'll get a massive kickback moment. Depending on the stiffness of the diaphragm, the less stiff, this bending moment diagram adjusts. And if you have a very flexible diaphragm, no diaphragm at all, it just reverts back to a cantilever bending moment diagram. But the thing about the problem with this kickback moment is what you end up getting is the slope of the bending moment diagrams is shear, and you get very large shear forces in your basement walls or the walls below the transfer level. And as a result, you get some the actual accommodating the shears and the diagonal struts in the lower walls is often significantly more difficult than dealing with the shear in the main wall above the transfer level. Another one is the stepped diaphragm. Try to avoid these where we can, but sometimes you can't, so they require a bit of additional structure. When you've got a change in height in your diaphragm, Build to Rent in Auckland's an example. How they got around it, this is a step section through the diaphragm. They put the main diaphragm through at one level and did a built-up wear slab above that to get the steps they needed for the architecture. So that was one solution. Another one, which was a very large effect, was a stepped diaphragm here. And this is a cross-section through it. And the red arrows are the diaphragm forces, which causes a moment couple of the blue arrows. That means we needed some structure to take out that reaction. And step 4, the detailed designers, you had to do a pretty good comprehensive strut and tie to get those load paths to work. So that's how one of the ways to deal with step diaphragms. Now we're getting into preliminary design. You can actually treat it as deep beam or a beam analogy, or macro strut and ties. Start with the macro strut and tie. Do not rush into doing the computer modeling of the grillage. It's very tempting because the computer models, it's the sense of being convenient, though often it's a lot of work to set it up. Start with the macro strut and ties. Identify the preliminary requirements for where do the struts and ties land? What are the collected elements likely to be? Do we have to accommodate unavoidable steps? Start thinking, how thick should our topping be? And ironically, how thick should our walls be? Because the biggest problem we usually find this happens at the end of the design. Someone goes to put their starter bars in, their HD16 starter bars, and they don't have enough wall thickness. So you might want to think about what's my starter bars likely to be, what my collector bar likely to be. That will affect your wall thickness. You want to sort of sort that out at the beginning of the design, not at the end. The beam analogy has been around for years. which is fine. Treat the floor as a horizontal beam. But here's a takeaway for you. This is a quick check to make sure that we're sort of getting in the right order of diaphragm thickness and so forth. It says use with caution. Consider the shear stresses at those locations. Simply the shear force divided by the thickness of the floor by the length of that interface, the beam depth in effect. If you've got 1 MPa, you probably won't have, as a nominal stress, V upon BD, you probably won't have too much of a problem getting it to work. 2 to 3 MPa, it's working a little bit harder, but probably doable. 4 MPa, well, yeah, that's diaphragm's working too hard. And if it's 6 MPa, you're outside the code allowable limits for struts anyway, so you're in serious trouble. We do not want to end up here at towards the end of the design. In other words, try and get these parameters sorted out early. I always laugh at this. How does the beam analogy apply when you've got walls on the back boundary and frames on the front grids? Deep beam doesn't really work. That's why strut and tie was sort of invoked. The code lays out that the codes, the earthquake code suggests using strut and tie. 3101 says you are required to use strut and tie for your diaphragm design as part of the compliance pathway. And the strut and tie is laid out in how to do strut and tie is generally laid out in Appendix A. Also in the loadings code, it points out to that diaphragm should remain elastic. We don't want to assign large ductility or any ductility if we can avoid it to the diaphragm. Also, too, when we do loads into the diaphragm, we use capacity design to make sure that we've sort of got an upper bound actions going into the diaphragm. So it says in the standard, localized plasticity within the body of the concrete diaphragm may be permitted. So the question is, do we introduce fuses? Plasticity? No, we try not to, but localized plasticity is okay. And that, as it says, it's typically things like where elongating beams have stretched the floor plastically locally at the corner. That sort of plasticity is fine, but you don't want to have a diaphragm which has a plastic hinge, the depth of the floor in it. Strut and ties models some of the basics must be in equilibrium. We use that method, as I mentioned before, at the moment in the code to come up with your floor forces. And the other thing, internal forces in the diaphragms, that's the inertias and so forth, as well as the, that's the tensions and compressions in the diaphragm must match the loads that are being applied to the diaphragm. So before rushing your strut and tie, get your boundary conditions, your boundary loads in and out of the diaphragm sorted out first. When you step back and look at that, the strut and tie almost jumps off the page. Just a couple of extra notes. Obviously, strut and ties must be proportioned so that the stresses of the nodes are acceptable. I mean, that's code language for make sure there's enough concrete to handle the compression and make sure that you've got enough steel for tension, which is properly anchored within or beyond the nodes. Macro strut and tie. This is where we start. Typically, the quite simple diaphragms, you can just simply do it with strut and tie without having to get into grillage modeling at all. So we start with macro strut and tie. It gives us a strong feel for what we would expect from our computer model. This is about one of the only places I'll mention mesh. Mesh can't be relied on, as we know, and it's written up in the guidelines, to rely as a tension provider because simply it's typically too brittle. So what we do is if we've got a mesh situation where that's the only reinforcing in the floor, you would default to a macro strut and tie, meaning you look at what your primary and secondary beams are doing is acting as ties, and you just ignore the mesh. Where can struts and ties land on the vertical lateral load resisting systems? At the corner or intermediate columns? We'd normally say no, but now we can also say yes. It's introducing a newer idea, old idea revisited. We'd normally say 25 years ago, land your compression struts in the corner of your frame, that's okay. Then we said, no, you can't do that. And this is the reason, and this applies today still. You cannot land struts on columns when precast concrete floor units are concrete topped. This is precast floor units and primarily is what I'm saying, along with, as well as, short starter bars lapping to cold drawn wire mesh, or cold drawn wire mesh acting as the starter bars alone, which describes a lot of our older style reinforced concrete buildings with precast floors. Just a bit of a step sideways momentarily for an example of the sort of problems we have in the corners of buildings. Clarendon with moan resisting frame on the perimeter, we're looking at that corner. That white column is that column there got pushed out of the building by the elongating beams indicated by the red arrows. And this is the sort of crack that we got, up to 35 millimeters, and the mesh up there with the arrow you can see is fractured. So this is a typical problem for these sorts of buildings. What we end up is with wide cracks, and we lose the ability to put struts across the floor. Tension still is available. Tension can still go across the those cracks. Now let's flag that up. The missing column tie is quite a critical feature. So it was suggested in 2010, this is what the crack patterns might look like, and you might not be able to land your struts on those cracks. It doesn't leave you with a lot of concrete. This is what the yellow C5 says. When you have no yielding, you don't have a wide crack. In other words, you can put struts across the floor into the corner column when you don't have a yielding frame. Now, there's a lot of words here, and it talks about the lengths of cracks in different situations. I will jump straight to the picture that backs up those words. What it says is when this beam hinges and pushes this column out, the crack length is 2 HB long, and it's also H, which is the crack width across there. Similarly here, this column and this beam pushes this column out, so that's 2 HB. This beam here pushes this column away from the building, so that crack is 2 HB. Where you do not have a column pushing, you don't have a beam, pushing the column out of the building, the crack is just HB, half of that. That's what that paragraph says on the previous page. Now we're just going to deep dive into this momentarily. It says, I'm going to read it out, which I'm not very good at. If a wide crack is not crossed by anchored, deformed ductile reinforcement, the 4671 reinforcement, then it should be assumed that the force transfer across the crack is ineffective beyond yield for 2 HB or HB, depending where it's located. On the other side, if the wide cracks are crossed by anchored, deformed ductile reinforcement, it may be assumed that the force transfer across the full length of the crack becomes ineffective at industry drift of 3%. That is, the ineffective length can be linearly interpolated. That's a lot of words. What that actually means is that in certain circumstances, struts can actually transfer through parts of those cracks. Now, don't worry about this. Here is for your notes when you get the PDF for this. What that means here is when I have a displacement which is below yield, my crack is fully effective. There's no ineffective length. If I got my frame up to 3% yield, drift, should I say, my crack is fully ineffective. In other words, I can't get my strut across that crack for 2 HB. And if you have a drift at 1.5%, you can come back and work out what the ineffective length is. And that's sort of demonstrated in this example. 0.7% yield drift, 1.5% ULS drift, the target drift. You plug it in, and what you come out with is that 0.7 HB away from the columns, you cannot land a strut on. That's what that red section is. So that's quite a useful tool for working out where I might be able to land my struts, particularly in assessment. And I'll talk about new buildings in a minute. It's not so much of a problem. But what it says is if you've got a ineffective crack, part of your crack's ineffective, you can bring the struts through the beam strut and tie through the beam in a horizontal sense to the corner column. You can actually use the plastic hinge to transfer the load across. Similarly, for interior columns and frames where the floors have been torn apart, you can strut and tie through the beams. These ties obviously have to be off the main, out away from the ineffective crack length for both new design, possibly. Assessment of existing structures and design of retrofits. Think about where your ties are. Also a reminder, you need to check the strut and tie path across the beam to make sure that it's actually viable. Usually it is. Just taking a step back for a moment, remember to take a look at the whole of building, the whole floor plate, not just concentrate on the corners or the particular load pass, because when you step back like this and look at the whole, you get the whole effect of the building, you get the complete strut and tie, the complete equivalent truss sorted out. It completes the picture. So what happens with in situ reinforced concrete suspended floors? That's no precast. The modern link slabs between hollow core units and the main reinforced concrete beams, as per 3101, one of the solutions for dealing with hollow core at the time. By the way, rib and timber infill falls into this category as a link slab. What about topped precast units such as T's and double T's? Here it is. It can be assumed that the compression strut can land on the columns as nodes, directly to the columns or immediately to the beams next to the columns, or basically that column, if the following provisions are followed. In other words, yes, you can do this, providing the starter bars are anchored to form ductile reinforcement, the 4671. This includes continuity bars over intermediate beams. The starter bars are not lapped to cold drawn wire mesh. There are existing column ties exist. Columns are tied in. This is all part of your tie for your strut and tie. And that interface indicated in red is either that whole area is in situ concrete, in other words, the topping, the beam column joint, and the top of the beams all cast at the same time. Or if the beam is precast or the column is precast and we're casting concrete up against it, those interfaces in the precast are roughened to 5 mils amplitude. So we're now sort of getting into the preliminary design side. We can use macro strut and tie, or often if you feel comfortable, you can go to a micro strut and tie grillage model. Around about this time, we are locking in the sizes of the collectors, the structure to accommodate unavoidable steps, topping thickness, and wall thickness. Just a little bit on the grillage, micro strut and grillage. These are useful for large diaphragms with significant voids. They can also be used for the simpler diaphragms. Remember that micro strut and tie, the grillage is not a replacement for complete substitute for macro. The macro gives us an idea of what we should have expected from the grillage model. So that's the recommendation. Start with your macro, refine it where you need to because of voids, re-entrant corners with your grillage analysis. And guidance on that is in part C5. We do elastic analysis of the grillages using software such as MicroStrand, and what the idea is, the grillage is meant to mimic a solid plate for bending and shear and the material properties. Here's some of the flags. Here's some of the things we need to be concerned about when we do grillage. The grillage is supposed to be a square. It's supposed to be squares, not long rectangles or, heaven forbid, truncated triangles. In a commercial building, a grillage should be around about 1 meter. That gives you about the right sensitivity, 1 meter squares. The diagonals in our New Zealand way of doing things, the diagonals are compression only, no tension, and the orthogonal elements in your grillage both have tension and compression. If you've got the situation where you think a corner column's being pushed away, yeah, that's understandable. So what we're recommending is maybe that diagonal there is taken out of the model, just to sort of make sure that we're not packing up anything into that corner directly if you can't get the strut directly to the corner. I just want to talk a little bit about some of one of the modelling techniques that's available out here, out there. This is a walls up here, walls here, concrete moment resisting frame here with structural steel and columns. It's an older building, and an annex sort of floor area flapping out here outside the main structure. I'll just point out, heaven forbid, this was in the early days. This is not a really good example of how to set up a grillage in terms of the squares. I've broken some of the own rules from 2 slides ago. But what I want to put up was the next few slides is what I actually want to focus on. Firstly, where do we put the inertias? We put the inertias on all the common node points of the truss. So there's our inertias applied across the floor plate, and these inertias are the inertias associated with the floors, beams, columns, braces, facades, stairs, and so forth at their particular locations. We apply the external forces, the forces from the vertical structure to the nodes where they are associated with, both in and out of those, in and out of the building. This model also sets up, the model we're suggesting is, this is a big flat floor plate in the computer, just floating in space at this point. So we set up 2 dummy nodes to act as stabilizing points for the software algorithm. These have very low stiffnesses and should not attract too much of any forces. If you get large forces in these dummy nodes in your computer model, it means you've put some forces in the wrong direction and you haven't got equilibrium. Everything's in equilibrium. The forces in there should be in the low tens of kilonewtons, if that. Part of the modeling too is this is a 4-plate floating. So it's in and out of the page, it's fixed, the Z-axis, but in the Y and X-axis, it's floating, and what stabilizes it, all these nodes here have this sort of support in the model, but these 2 dummy nodes stop the thing flying off mathematically. Just a bit of a worked example. This is the Majestic Tower in Wellington. This is the ETABS type model that we put together for the structure. It's got walls in the center and big heavy duty concrete frame on the perimeter. This is one of the grillage models that was set up, and the dummy nodes. As you notice, it's quite a high intensity of nodes. This is like a poor man's final element in some respects. The size of the grids, the actual boxes, I said 1 meter, but what you often do is pick the grid so you end up with a sensible number of squares around your penetrations. Now, you don't get too worried about your grillage matching the holes exactly, as long as they're within sort of half a box overlap into the actual hole or outside the actual void. It doesn't matter, because you're going to have this, you're going to be taking stock of all these assumptions along the way. So don't get too worried about if your grillage does not match your holes exactly for dimensions. This is another example of another grillage for the Majestic. There's the forces from the structural analysis being fed, the floor forces being fed into the grillage model, both on the perimeter and in the walls. I mean, the walls are pushing loads into and out of the floor, so that has to be part of the model. Yeah, this was the early days. This is these notorious triangles I was talking about. Yes, if you do that, fine, but just be aware you've done it, and you develop a sense of whether it's critical or not. There's another version of it. This is the one we've seen before. And in this case, the designer did not use the triangles. What he did is a very relatively fine mesh of squares, of grillages, and that in itself is close enough. It doesn't, to modeling the edge of the building, because you do that consciously and say, well, does that have an effect on my actual load path? You assess it at the time. This is a snapshot of some of the results. That's the wall in the middle of the Majestic, and the green box is the tension of the diaphragm builds up, builds up, builds up, builds up, and maximizes going into the wall. This is one of the lovely things about the grillage model. We'll just blow that up. There it is. The tension in the collector going into the wall builds up, and you notice that the tension in these members drop off in the grillage, which sort of gives you an indication of the effective width of the collector being involved. So it's quite a nice way of giving a feel for where the loads are going in your floor using this method. Appendix C5D of yellow C5 gives us the dimensions. The members' dimensions come from Hrenikoff's PhD. It's an idea of giving you an equivalent stiffness to a solid plate. In New Zealand, on the diagonals, we have no tension on the diagonals. One of the things is that you find is there's a lot of information here. I'm just going to leave this here for your information, because you can read it later. But the diaphragms, if you look down at the bottom of the page, the diaphragms have different thicknesses, whether they're running parallel to the units or transverse. And so there's recommendations on different floor layouts for along the units and across the units, parallel and transverse, in terms of the thicknesses you put into your model. Heads up, this is a warning, a friendly warning. When you check the stresses at the nodes, like on your columns or along your beams or at the ends of your walls or along your walls, use strut and tie. A lot of people have been trying to automate the grillage to give you the answer. Well, that really, if you have a coarse grillage, very large grid spacings, it all goes to hell in a handbasket. You don't get a good idea of what your stresses look like at your nodes, where the forces are actually entering and leaving the vertical lateral system. Don't use the Hrenikoff dimensions for working out stresses. They are simply a means to an end to give you about the right stiffness. Don't use the Hrenikoff 0.63 grid as a dimension for checking stresses. That's an absolute don't do it. What you do is you work out you can work out your forces from your grillage. If you want to, and I like to draw a strut and tie over the top of it to confirm that everything's going okay. If you've got a wall or a column, you actually work out the forces and you come in and do a strut and tie on that node from first principles. Just one of the examples that's of a nightmare situation. A winged building with two wings and holes right in the critical part of the junction. Compression's blue, tension's yellow. How do we get those compressions through that part of the floor, which is now full of holes? So what they came up with is those particular parts of the floor, they thickened up and turned into columns. So that thickened floor can handle the tension and compression in that reduced section. So that's the sort of detailing that you're going to have to employ when you've got these unusual architectural demands. Collectors. We're on our last couple of three slides, ladies and gentlemen. I want to just highlight collectors. What stiffness do you put in? If you've got on your grillage a collector, one of your lines of your grillage is a collector, what you might want to do is actually put the realistic stiffness for the collector, and it would be RC beam area plus some flange, structural steel girder plus some concrete flange, or it's an area of slab that's chocker full of reinforcing. That particular area of the collector is solid, and what we're recommending is you use A gross or A gross transformed, transforming the steel to concrete. Even though these might have cracked, they're still largely, the amount of cracking small, so they are largely still relatively stiff. So that's what we're recommending. And you may find, as it says here, you may have to go in manually and put those properties in on those grid lines for those grid elements manually, rather than let the computer automate it. Watch out for collectors. There's about there's three different types. There's the collectors that go into the walls, and one side will be in compression, the other side will be in tension. That's pretty obvious, and the tension and compression increases towards the wall. You also find if you're using gravity, if you're using seismic resisting frame beams, which are gravity and seismic, they're also going to be carrying, can carry and will carry some of the axial tensions and compressions from the collector type or chord behaviour. So what you tend to find is that one end of the beam's got a bit more tension in it, one end has got a bit more compression. I'll come back to that in a minute. And there's the other ones where you've got pure collectors, which has just been completely stretched. And these tend to have a reduced flexion and shear capacity for carrying gravity. So things we have to worry about is redistribution of gravity loads when you get these axial forces, softening or potentially weakening parts of the beams, reduced or increased, reduced plastic curvature capacity, increased plastic curvature demand. Think about what your detailing looks like if you're going to, in terms of like we did with that slab that the boys had at the corner with the holes, and the impact on vertical lateral load resisting capacity and performance. The axial loads have an effect. Now I'll just put this up, that if your axial load ratio in your beams is below AG of F prime C below 0.15, 15%, it usually doesn't matter. If the axial load is quite significant, it does matter in terms of reduced capacity. But this one here, I like this here. If you've got some tension here, your overstrength moment has reduced. But if you've got similar compression in the same situation arriving at this end, your MO, the overstrength moment, has increased. So when you go along the entire building, you find that the overall capacity of the system hasn't really changed. It's just redistributed. So it's usually actually not a problem. And that, ladies and gentlemen, is the end of the presentation.
Thank you so much, Des. That was a lot of information. And again, thank you on the amazing presentation. Now we're moving to the Q&A section. So we go through the Q&A in terms of popularity. And trying to update this. Just a moment. Okay, we'll go with the first one. Could you provide some comments on diaphragm strengthening methods, such as the use of FRP?
There's a lot of really good work being done out of the University of Auckland at the moment. On coming up with recommendations for using FRP. FRP is a good system for providing tension capacity. There are tricks. It's always in the detailing. Let me put it this way, it's definitely viable, it's still work in progress, and I think in the near future we'll get some very good recommendations out of the University of Auckland on how to achieve it.
Thanks, Des. So the following one from Cheoryu, he asked, I don't know, could you provide some comments on traditional Grillage diaphragm analysis versus finite element analysis by software such as ETABS, and why most of engineers still prefers the Grillage method?
That's a good question. He's dramatically saying, right, I've got a slide there on the screen, hopefully.
Yes.
Yep. It's very useful, and it's a very useful technique. It gives you really good answers. But in terms of complexity of using the material, using the method, setting it up takes a lot of effort. It may be warranted. Getting answers out of the finite element, you have to take sections through your stress contours and basically integrate those stress contours. But there are now post-processors that will actually do that for you. Some modelers will actually model the reinforcing bar explicitly to get direct outputs on terms of the tension that these bars are feeling, which is fine. It also includes areas of inelasticity. If you've got that sort of problem, this is a great way of capturing that, if it's significant or not. But as it says in the last bullet point, it's not a general tool. It's a good tool, it's a great tool, but it's not a general office tool. You usually find specialists with a lot of skill are needed to do that, to use that technique. So mainly people use Grillage is that it's simpler. It's simple to use. simpler to use.
Awesome, thanks, Des. The next one from Hans. For nominally ductile or brittle structure, do we need to consider concurrent or skewed earthquake actions, 100% plus 30% using pseudo-equivalent static analysis loads, and why?
That's a really good question. The camp's 50-50 on that. Yellow C5 says you do. That's the current Yellow C5 says you do. There was the earlier version of C5 says you didn't. And so without using up precious minutes explaining why there's two differences, at the moment, the current guidance says yes, you do. Do you get any significant value out of doing it? Probably not, in terms of finding more critical cases. You're far better, seriously, you're far better to apply earthquake loads north, south, east, west, and then on the 45 degrees. That would give you, in my mind, a better sense for where the loads are going inside the structure than rather than 130. 130 is not a get out of jail card, but you are required to do it at the moment.
Right, that's good to know. From an anonymous attendee, the question is, we just moved. Why not use finite element methods? I think we talked about that, but shells, like they do it. Sorry. Why not use finite element methods like a shell, like they do in North America? You can see that the NEHRP recommendations, this Strut and tie seems very prone to human error and hard to peer review.
I mean, I agree. Strut and tie is not a forensic tool. It was originally, it was introduced in New Zealand as a design tool because back in those days, people basically just had rigid diaphragm models. They didn't have the plates and so forth we could put in. So when you sort of look at the evolution of these things sort of leapfrog over each other. If the practitioner understands that software and can actually interpret it correctly, great, go for it. If it gives a higher resolution, more confidence in where the load's going, absolutely. But the grillage analysis was developed for a situation when people did not have access to that sort of software. So by all means, you've got better software, use it.
Right. Now, the next one, I think you talk a little bit about this, but how do you handle vertical steps in the diaphragms? For example, in an old building, they somehow have a 300 millimeter step between the balcony and the internal slab. And just to clarify here, it says that this is a DSA situation, so we don't have the opportunity to locally thicken the slab edge like you show in the slides. You simply delete the struts and ties in the grillage model? Is there a better way?
You end up finding yourself in two situations. If you've actually got a step in the diaphragm, like forming a Z, you would actually track the loads through that horizontal, vertical sub-wall and back into the next diaphragm. And basically, it's behaving like two beam column joints above one another. So there's a strut and tie solution to that. Yep, and people have done it and made it work or come up with a rating for that. If it doesn't work, then you're into having to either cast some new concrete underneath, or the other ones we've done is bolt steel girders at 90 degrees to the wall, to the step, to basically give some backspan, outrigger type behaviour. We actually post installed that sort of detailing you're seeing there.
Yeah, that makes sense.
So you can do it for first principles, or you've got to add some structure if it doesn't work.
Yeah, thanks, Des. The following one from Kelly Mayer. Hi, Des. What is your opinion on using reed bar inserts in lieu of bent starters bars to transfer forces from the diaphragm into precast panels?
Well, fundamentally, particularly with the modern situations that reeds have been developing, it's a pretty good option. The new reed couplers and inserts are good options. The only thing I'm saying, and I'm pretty sure reeds are all over this, but we do this anyway. The embedded length depth we run a Chapter 17 3101 to make sure that for shallow embedded item pull out, pry out has been met by the dimensions of the item, whether it's Reed's or anyone else's. We just run a quick Chapter 17 check. A lot of the literature coming out now says we have done this to Chapter 17 and we will get up to the rupture strength of the bar, which is what 3101 requires. It's not yield. Don't do the check at yield. It's actually FSU we're looking for out of those bars. That's a 3101 requirement. And the older guidance used to do all the HEF, the embedded item depth, based on yield. So they're all too short. But a lot of the modern inserts and couplers have caught up with that. It's something to keep an eye on, that's all.
Yeah, oh, that makes sense. From Erickson and Sina, what reduction can be applied to diaphragm stiffness? Oh, the question just moved. Give me a second. There you go. What reduction can be applied to diaphragm stiffness to obtain the effective stiffness when modeling? Any recommendations to account for realistic diaphragms, including the topping, beams, and collectors? Especially for the topping or solid slab when used, and different stiffness of the elements when acting in compression and tension.
That's a good fundamental question. The grillage analysis is attempting to take that into account. We know this could be a really long or very short answer. The grillage analysis and everything that's on the slides, and I'm not being sarcastic, basically is attempting to answer that question. The comments, the last ones I flew through at the end, the collectors about getting the right stiffness and using A gross to get the right stuff so it attracts the right amount of load. This is reflecting the relative stiffnesses between the diaphragm, the slab, and the girders which are acting as collectors, whether it's steel or concrete. What we do know, and this goes back to Debbie Gardner's now, Mrs. Shearer, Dr. Debbie Shearer's PhD, was if you include tension in your concrete, you get a totally different distribution of forces. It's actually quite helpful. Things are less stressful, less harsh. But what we don't know is we can't predict when the cracks are going to occur, how far, what the extent of the crack, what the loss of stiffness is. So the crude method, which is the grillage and strut and tie method, says we just assume concrete's cracked. What that does is give you the maximum upper bound tension loads in your tension steel for your ties. So this is a way of bounding it. It's not a forensic tool. If you need to get down to that level, you need to get into the nonlinear fauna element.
Yeah, here Timothy Blackburn expand a little bit on that. So ACI 318 has some guidance on this. 2019 version suggests a 0.25 crack section modifier. We'll be keen for the presenter's thoughts on this.
If I've understood the question, when you do your computer, I may have misunderstood the earlier question. When you do your computer model, your 3D model of your whole system, you would, using the ACI or ASCE section modifiers for diaphragms is a really good place to start. Your diaphragms, you're not I gross, A gross for your diaphragm model in ETABS. Go and actually use those ACI or ASCE guidance for stiffnesses. That will give you a realistic distribution of forces through your floor plates and up into your vertical systems. And then you transfer those actions into the strut tie grillage model that we're doing here. So yes, definitely model this using those ACI recommendations is a good place to start.
That's great. Now, the pseudo-equivalent static analysis load accumulation at transverse diaphragms tend to become incredibly large. Is this real or just an accumulation of the simplified method? Any suggestion how to deal with it?
Do me a favor, say that one again. I was anticipating something else, and I've got myself lost. Try again for me.
Yeah, that the pseudo-equivalent static analysis load accumulation at transverse diaphragms tend to become incredibly large. Is this real or just an accumulation of the simplified method? Any suggestions how to deal with it?
There's two aspects to this. I think the word transfer threw me a little. If you use the Pisa method up to about 9 stories, what you get is reasonably realistic loads being applied up the side of your building. Where we get into trouble is taller buildings, which is work in progress. There is a working party at the moment looking at what we do with taller buildings for diaphragm loads. That's undergoing at the moment. That's good news for everyone. This is coming. This is to get around the 9-story cap we have in the code at the moment. The problem is on high drift buildings or low seismicity buildings, you find the PGA ends up being up the whole side of the building. This gives an artificially high lateral load to the problem of working at diaphragm load. So there is a problem. So that's being worked on. So that's where I'm going is I don't have a solid answer for that question. The other side of it, which is, if I misinterpret, is the transfer side. This comes down, how big your transfer forces are comes down to the stiffness of your diaphragms, which is what we spent a few slides on. But at the moment, Pisa will, for certain structures, give you significantly larger loads than you probably need to be dealing with, above 9 stories and in low seismic zones. So that's work in progress. It should be coming out shortly. I'm not doing it directly, but I'm aware of it.
That's good to know. Thanks, Des. I think we're just in regards of the time. I'm gonna go through the other questions a little bit quicker. Strut and tie, I think you already talked about how we can consider using shells instead of the strut and tie method. Could you kindly explain whether we should consider prism, strut, and bottle strut in a strut and tie model?
Oh, I mean, that's a whole nother 116 slides. You definitely, depending on the situation, some struts will naturally form prisms, rectangular type struts. That's sort of like in the struts you get in a reinforced, well reinforced concrete beam. But when you've got flat slabs or deep, very deep beams, the struts tend to form bottle struts. And there's a bunch of rules in 3101 on how to detail and deal with bottle struts. Some simplifications in terms of doing the stress calcs, which is nice. And basically, it's the same as the prism, same stress calcs as prisms. But when we come to detailing orthogonal steel in walls or deep beams, there's a bunch of special requirements for areas which have bottle struts in them.
Yeah, that's a really good answer. Thank you. Can we rely on PT in post-tension slabs and the compressive stress in the slabs to reduce the tensile forces in the tie members?
Yes, you can. Depending on the situation, if your stresses are keeping within the service load range of the PT floor, yeah, it's just an extra load in a PT problem. If you've got very large forces and you're pushing well outside, you're starting to get up towards your yield of your PT tendons or strands, then it's just really a conventional reinforced concrete problem with very strong steel. So depending on what level of earthquake you're looking at, yes, the PT can help the performance of the floor, definitely.
All right, thanks, Des.
Oh, by the way, the PT is put on as a external load. When we talk about the loads we put on the floor plates, the PT, if you're thinking about how to take into account the presence of the pre-compression, you'd put it on as an applied load on the diaphragm, and that will change the shape of your strut and tie solution. Yeah.
From Tom Lindsay, most precast floor systems with a topping generally end up with cracking over the supports as the topping tries to make adjacent spans continuous. Do we need to account for these tensile forces in addition to the diaphragm inertia forces when analyzing a diaphragm? Sorry.
Do me a favor and say that one again.
Yeah, most precast floor systems with a topping generally end up with cracking over the supports as the topping tries to make adjacent spans continuous. Do we need to account for these tensile forces in addition to the diaphragm inertia forces when analyzing a diaphragm?
That's a really good question. The fact that most precast, respective precast floors, probably not. Most precast floors, when they cast, will support their own weight, the weight of the topping, and some construction loads. So what you find is that cracking, yes, when you put a bit of live load on, that might help, might widen that negative moment crack, but that crack actually predominantly starts from shrinkage. And so, yes, those starter bars are being stretched initially. Typically, they may be even near yield, but where the industry sort of settled on this is, for precast floors, do not worry about the gravity effects on the continuity or starter bars. Just assume that they're not there for the tension field. But if you've got an in situ floor, the answer is yes. If you've got an in situ floor, which is relying on the top steel to provide moments for gravity support, the presence of axial tensions in the floor will diminish the gravity carrying capacity of a purely in situ floor. Yes. Not for precast, but for total in situ floors, yes. Worry about it.
For Marco Chui, do you have any advice on where to put the dummy nodes in the Strut and tie model? Will it be best to align this with the lateral load resistance system?
No, that's actually a good question. It's normally not too critical, but what we tend to do is keep them very, like in the middle of the center, lined up with the center of mass and quite wide apart. Wider apart, the better. It tends to just help them stabilize the mathematics. Line up with what in terms of the 2 points, center of mass in the middle and wide apart is usually a good recommendation. Well, what we've also done in the past is one of those dummy nodes is fixed in all directions, and the other one is allowed to roll in the direction of the earthquake. So there's actually no restraint. But if you pick a low enough stiffness in the dummy nodes, just to complete the mathematics, you can have them fixed on very soft springs. For all direction, it should be fine.
That's good. Thanks. Des, probably we're going to go for the last questions. We've been asking you a lot of questions. So, can we use elastic grillage model for assessing diaphragms with non-ductile mesh and use the mesh tension capacity reaching strain of 0.003 for the orthogonal members to determine the rating?
The answer is no. So let's go with no. The reason this is that going back to 1994 earthquake Northridge in LA, when they opened up a number of buildings which had mesh in them, they found that the mesh between every unit was fractured. Every wire on between every precast unit, all the mesh was gone. And so that was the first. That was Neil Irvine and others found this. That possibly these were in car parking structures, so car traffic and heat and cooling of the day caused high cycle fatigue on the wires. But they opened up other ones. We did this here in 2010, 2011. Opened up floors to find in the middle of the floors the wire mesh was broken. So it's generally between units you can't rely on it. If you've got mesh that's the continuity steel, starter steel or continuity steel, you definitely can't rely on it. There was some thought that you might be able to use the mesh running parallel to the units up to the starter bars, because essentially it's not shrinking and not being affected because it's just sitting on top of the units. But that has a limited capacity, because once you get about 1% rotation, a negative moment of 1% rotation, you find that the topping delaminates. And delaminates about 600 mils all out to the end of the short starter bars, and the mesh breaks. So when we added all this up, there's very, very rare cases, very narrow band of cases where the mesh may still be intact. As a general rule, it is not. So that was my slide referencing just when you've got mesh, ignore it and just go to macros. Use your secondary beams and your primary beams as your picture frame for your strut and tie, and ignore the mesh. To be honest, that's where we are now, and I stand by that. I was literally thinking about that this morning. There might be 1 or 2 cases, but they're extremely rare. I knew this question would come. They're extremely rare. So it's a general rule. The answer is we don't, and it's in the yellow C5, we don't rely on the mesh in these systems.
That's very good. Thanks so much, Des. And thank you so much for all the information that you share. Your knowledge has been very, very helpful. And by seeing the numbers and the amount of open questions that we still have, I understand that all of the people are really appreciating the knowledge that you shared today. For all of you, the SESOC members that are joining us today, thank you so much again for being part of this, for asking your question. We will be distributing all the slides, and the recordings of this webinar will be available in our YouTube channel. So you can check our YouTube channel, and we will provide the links for that later on. So thank you again, Des, and thank you, everyone.